Hello IB students. So I just want to take you through the May paper from 2021, the paper 2. So we'll just go through the questions and how to answer them together. Now note, I don't actually have access to the formal mark scheme at this point or the formal answers. So these here is my best guess at what the mark scheme is, and these are my answers here. We're starting off with a question about a football player, and there's a wall. And they're kicking this ball on an angle. Now we're being asked to calculate the average force that the player exerts on the ball if the ball is originally at rest and then it comes to a speed of 19 meters per second in 55 milliseconds. So in this case, to calculate our force, we've got F equals ma. We need to calculate our acceleration. So acceleration here, we're just going to assume that we have a constant acceleration, so we can just use acceleration equals the change in velocity divided by time. So if you do that, your final velocity is 19 meters per second. Your initial velocity is 0 meters per second. You divide that by the time that the ball was in contact with the foot, which is in milliseconds. So 55 times 10 to the minus 3 seconds. And when I put that in the calculator, I get the acceleration is 345 meters per second squared. Now I'd anticipate that's what the first mark is going for here, and then the second mark, you just put that F equals ma. So we got 45 kilograms, or sorry, 0.45 kilograms multiplied by 345 meters per second squared is the acceleration, which makes 155 newtons. So that is 1A. We have a look at 1B together. So 1B, I've got to admit, this one's got a bit of diagrams and things to it. So what I might do is I'll just clean out the board and do a new one. Okay, so we've got the ball coming up at this angle here. We've got 22 degrees, like that, from the ground. We're being asked how long it will take to get to a wall, which is 11 meters away. So somewhere over here, there's a wall, and that's 11 meters from where you start. Now, this is essentially a projectile motion question. And for projectile motion questions, the horizontal component has no acceleration. So acceleration is equal to 0 in that, if you like, or another way of thinking about it is you just use your constant velocity formulas. So when we're dealing with constant velocity, the displacement is equal to the velocity multiplied by the time. So just note that this is the velocity in the x direction here. So I've got that the overall velocity on that diagonal is 19 meters a second. I need to figure out what is the x component of that. So I'm going to call that Vx. So to figure out my Vx, it's going to be equal to 19 meters a second multiplied by the cos 22 degrees, which I've previously calculated to be 17.6 meters per second. So then the time is going to be the 11 meters. So I've got to rearrange this equation for time. So time equals s divided by Vx. Divided by 17.6 meters per second, so that is 0.62 seconds. And that's the answer that I got for that one there. I would assume that 1 point goes for doing your vectors and finding that x component of v, and the second point goes for finding t there. Okay, so if we have a look at the next part of this question, the top of the wall is 2.4 meters above the ground. So, okay, over here I've got my wall, and I'm told that it's 2.4 meters tall, essentially. Deduce whether the ball will hit the wall or not. Okay, so just note, in the previous question, I've already found the amount of time it's going to take for the ball to move horizontally to get to this here. So then the question is, I just need to look at the vertical motion. At that time, which was the 0.262 seconds, will the ball be above or below that wall? So essentially now, rather than being a 2D problem, I'm really just thinking about, okay, the ball moving up and down, where is it going to be up to at that stage? So the way that I do this, I'm in the vertical direction, and in projectile motion, that means that I'm going to have a acceleration, a constant acceleration. So that means that I can use my constant acceleration formulas. In this particular case, I'm going to use s equals ut plus half at squared. But note, this is all in the vertical direction. So this is my vertical initial velocity, and this is my vertical wall, if you like. Now, in this particular case, we kind of have all of the variables that we need. So we've got actually everything. What I'm going to do is I'm going to use this to calculate how high up the wall it will be, and I'm going to compare that to my 2.4 meters. So we're going to compare those two answers and see if I get to clear that wall or not. So in this case, before I had a diagram where I was showing the velocity. So this is 19 meters a second to start with when it gets kicked. This was 22 degrees. So I want to calculate this component here. This is my uy. So that's what I'd like to find. So in order to do that, I'm just going to say that my uy, so looking at the triangle there, so the cos of uy, the cos of 22 would equal, let's start again. The sine of 22 would equal uy divided by 19. So that means uy will be 19 times 22 degrees. That's in meters per second, so times the sine of 22. And then I got that to be 7.11 meters per second. So then I'm going to put that into here. So 7.11 meters per second times 0.62 minus, so it's minus because I'm accelerating downwards due to gravity, so minus 9.8. That's meters per second squared multiplied by 0.62 all squared divided by 2. When I put that in the calculator, I get 2.53 meters. Now 2.53 is bigger than 2.4, so that means that my ball should be, at the time when it's at the top of the wall here, it should be higher up than the wall. Though notice it's really not much, it's only by 10 centimeters. Okay, so that's question 1b, part 2. Let's have a look at 1c. So we'll look at 1c now. And for this one here, it's just asking us to describe the effect of air resistance on the ball. So air resistance, I would say, always opposes the direction of velocity. So as the ball is moving upwards, this means that the air resistance would be downwards, which, as they've defined it, is a positive acceleration. So overall, the acceleration of the ball would be increased downwards. It would actually have a larger downwards acceleration because gravity is combining with this air resistance. Okay, so that's part C. Let's have a look at part D together. Okay, so for part D, now we've got the players kick the ball, and this time it's rolling on the ground. So we've got a ground here, we've got a ball, and it's moving this way, and it's kind of rolling as it does it. So it's coming around like this. So this is pretty much one of our circular motion questions. Thank you very much, topic 6. So we know that it's moving with velocity equal to 1.40 meters per second, and we know that its radius here, r equals 0.11 meters. They want us to find the angular velocity. So this one is relatively straightforward. We can just use our no slip rolling condition, so v equals omega r. So if we do that, we get omega equals v divided by r. And so that's 1.4 divided by 0.11 equals 12.7. And it's asking for an appropriate SI unit. Now, you could say radians per second. However, radians isn't actually a unit. It's like a dimensionless quantity. So really, this should actually come down to 2.7 seconds to the minus 1. That is the unit to put on your answer. So we're on page 4 now, and they've given us this graph of the pressure against temperature. Now there's a couple of things to watch out for, and one of the biggest ones is that they've got that the units of the pressure is kilopascals. So it's not a standard unit, it's times 10 to the 3. So we just got to take that into consideration when we do all our calculations. Now they've said deduce whether helium behaves as an ideal gas over this temperature range shown in the graph. Now, deduce means that we have to look at their data that they've provided us and show that it's true, or determine if it's true. So, in this case, we're going to use our ideal gas law to see if it's an ideal gas or not. So that's PV equals nRT. But really, what matters here is how does P change with T? So really, does P over T, if I divide T to the other side and divide V to the other side, so if this is staying a constant, or if this is staying a constant, then it's behaving as an ideal gas. So I just want to check for these different points, P and T, is that going to be true? Now note, I could actually have my T up here on the other side. So if the T was up here, it would be like, is it a linear graph? So is P equal this T? And importantly, with a y-intercept of 0, 0. Now it doesn't look like a y-intercept of 0, 0 because we haven't seen the trace back here to where it would be. Okay, so I'm just going to calculate this ratio. For the point where it intercepts the x-axis, I get, so my P1 over T1 is equal to, so my pressure is 100 times 10 to the 3 pascals, that's pretty much atmospheric pressure, and I'm dividing by the temperature in Kelvin, so 250 Kelvin. When I do that, I get 400 pascals per Kelvin. Now I'm going to do it again with a different data point. I'm going to choose the point right on the right-hand side. So that means I'm going to get 200 times 10 to the 3 pascals divided by 500 Kelvin equals 400 pascals per Kelvin. As this is a constant, that's showing that it obeys the ideal gas law. And so helium is behaving like an ideal gas. Now, if we have a look at part B, from part A, the calculations I've already done, I know that nR over V is equal to 400 pascals per Kelvin. And they want me to calculate the mass of gas in the container. Now, to figure out the mass, if I know how many moles there are of helium, I can use the molar mass to calculate the mass, because mass is equal to moles times molar mass. And my molar mass is just 4 grams per mole here. So that means my final answer will be in grams. So let's do a little bit of work here. Let's figure out what our n is. So little n is going to be equal to, we've got our 400 constant, pascals. It's multiplied by the V and divided by the R, because I'm dividing the R down here and multiplying the V up there. So when I do that, that becomes 400 multiplied by, so the volume of the container is 10 to the power of minus 3. That's meters cubed, so I'm doing everything in SI, so that's pascals per Kelvin. And we're going to divide by the gas constant, which is 8.31. That means our final answer here is going to be 4.8 times 10 to the minus 2. So then I want to figure out the mass, so I take my 4.8 times 10 to the minus 2, minus 2 moles. I multiply by 4 grams per mole, and that gives me 0.19 grams to 2 significant figures. And that's how you do B. So now let's have a go doing C. So for this one here, it's saying there's a new container where we put twice as much gas in the same volume. So if we have a think about what this looks like, so this is what the container was. So the container was like this. But now there's twice as many things in there. So if we have a think about it, if the temperature is the same, that means these particles are moving at the same speed as these ones, but the volume is the same. These ones are going to be striking the walls twice as often, just because there's twice as many of them compared to this. So that means the pressure is going to be doubled at a given temperature. So for the same temperature, the pressure should be doubled. So if on our older graph, if we trace that back, because it's an ideal gas, this is our temperature in Kelvin, and this is our pressure, then if the old line looks something like this, our new line should still go through 0 pressure, 0 temperature. But now it should be much, much steeper, the line like this. It should be twice as steep, in fact. Now we were looking at a chunk of the graph that might have been over here. So this is where our axes were. They weren't at 0, 0. So that means we'd still expect this line to be here, but this other line would come through at a different point. So some key points that I would put in my answer for this is I would say that the gradient now should be twice as steep. So before I calculated the gradient, it should have been 400 pascals per Kelvin. Now the gradient should be double that. So it should be 800 pascals per Kelvin. The y-intercept should still be 0, 0. I'd say that's a really key one. And then if I was just to pick a temperature, so when I was at 250 Kelvin, that was my point kind of just as this was coming through here, then rather than being at 100 kilopascals, now I should be at 200 kilopascals. So that was just a point that I chose. Okay, let's move on to page 6. So question 3 here is a little bit of a nasty one in a couple of ways, but that's okay. The thing that I think most people are going to find confusing is getting all of these symbols correct, because there's lots of things that are E and sigma, but that's not what it refers to here. So they've given us a cool new equation that you've never seen before. This equation is the electric field strength is equal to sigma. So sigma is the density of the charge. So how much charge is there on this wall per square metre of wall divided by 2 epsilon naught. And epsilon naught is hopefully something that we are somewhat familiar with. It's the permittivity of free space, and you can find its value on the data booklet So they want us to show that the units on both sides of this equation are consistent. So really this is a topic 1. So let's have a look. So to start with, the definition of the left-hand, so it's good to do the left-hand side and the right-hand side and show they're the same. So let's start with the left-hand side here. Left-hand side, the units are, so electric field is essentially force per charge. So this is newtons per coulomb. And then a newton is a kilogram meters squared per second squared. And that's all over coulombs, so coulombs to the -1. So that's our left-hand side. For our right-hand side, okay, so the units are, we've got 2 different parts here. So first of all, we've got our bit on top, so let's do that. So this is the amount of charge per square meter. So it's the coulombs per square meter, or that should be meters to the -2, so I'll just quickly, coulomb meters to the -2. And then on the bottom of this, we have got 2 has no units at all. And then epsilon, so you can actually look this one up in your data booklet. So the units for it are c squared. If we do this, so one of the coulombs on the bottom cancels out with one of the coulombs on the top. And then, sorry, that was newtons to the -1 and that's meters to the -2. So our meters cancel out here. And so that means we've got a newtons to the -1 on the bottom. That's the same as having newtons to the 1 on the top. And then coulombs to the -1. So once again, that's going to be kilogram meters squared seconds to the -2. Alright, so therefore, left-hand side equals right-hand side, and the units are the same on both sides of the equation. That makes us happy. That's a units part. The next part is to do with vectors. So if we just draw an angle here, so we've got there's this thread, and so it's the ball is over here. And there's an angle between the vertical of the wall and the thread, that's 30 degrees here. And the ball has got a given mass, that's nice. Let's think about what forces are acting on this. So we've got this tension force from the string up in that direction. We've got gravity coming down. So that's mg, I guess, or the weight force, W. And then the charge is being pushed away from this wall because this is positively charged over here. This has got lots of positive charge on it. And this has got some positive charge on it as well. There's going to be a repelling force in this direction here because it's being pushed out this way. That's our electrostatic force. And they want us to find the horizontal force that acts on the ball. So they essentially want us to figure out how strong is this electrostatic force. Now that's, if we consider Newton's first law here, this ball is just sitting here. So that means the forces need to be balanced. So the vertical component of this tension force would have to balance out the gravity force, and then the horizontal component of the tension force would have to balance out this force here. So in order to balance these two out, first of all we need to figure out how big the tension is, and we can do that using our gravity. So to figure out how large our tension is here, we're going to look at this vertical component of it, so I'll just call that T in the y direction, and that has to be equal to our mg. So if we have a look, that angle's 30, so this angle is 60 degrees in here if you like. Now first step I guess is finding the gravity, so mg, so in this case our mass is 0.025 kilograms. Gravity is 9.8 meters per second squared, so that is going to be equal to 0.245 newtons. Okay, so now that I've calculated that component there, what I want to do is, I'm just going to draw this up as a triangle for a minute. So I've got this triangle, and I've just figured out that this component here is 0.245 newtons. That angle in the corner is 30 degrees, and I want to know this x component over here. So if we have a look at this, this is the opposite, and I already know the adjacent. So the perfect trigonometric ratio for me to use here is tan. So the tan of 30 degrees is going to be equal to the opposite to the 30 is x divided by my 0.245. So in that case, my x is going to be equal to 0.245 newtons multiplied by the tan of 30, which is equal to 0.14 newtons. Now, I just put an extra note on my answer here that technically the net horizontal force on the ball is 0. But there's a thread now exerting a force of 0.14 newtons to the right, to the left, and the repulsion from the wall is 0.14 newtons to the right. because they didn't actually specify which horizontal force acting on the ball. So now we're moving on to page 7 and doing question 3BII, and I'm just going to recall this previous result, the force is equal to 0.14 newtons. So then they want me to figure out what my charge density is, sigma. Now to do this, if I already know the electric field, this becomes easy because electric field equals sigma over 2 epsilon. I can rearrange that to find my sigma is equal to 2 epsilon E. But to do that, I need to find E. So the definition of the electric field is it's the force divided by the charge. Now I already know the force from the previous question, and they've just told me the charge on the ball is the 1.2 times 10 to the minus 6 coulombs. So in that case, I can just do 0.14 newtons divided by 1.2 times 10 to the minus 6, and that will give me 1.18 times 10 to the 5 newtons per coulomb. That's my E. So then I can substitute that into here, and that will give me my sigma is equal to 2 times my epsilon. Epsilon, if you look it up in the data booklet, is 8.85 times 10 to the minus 12, and then I've got to multiply that by my charge, which is 1.18 times 10 to the 5. When I do that, I get 2.1 times 10 to the minus 6. In this case, the units is coulombs per meter squared. Okay, and that's how you do part 2. Now let's do part C. So for part C, they're saying that we've got our original charge over here. So that one's our plus 1.2 microcoulombs. And then there's some point here called P, and there's some point over here called Q. And they've given us the distances between them. So there's this distance in here, which is 0.22 meters, and they've given us this distance from here to here, which is 0.4 meters. So we can actually use that to figure out this distance in here. So this distance is 0.18 meters. Okay, and then they want us to calculate the charge on Q. So there's some charge over here, such that the electric field strength in the middle here is 0. So to figure that out, what we can do is we know that the electric field strength coming from this must cancel out with the electric field strength from this. So if I call this one E1 on the left-hand side, that must equal E2. Then I can just substitute in the electric field due to a point charge is equal to K. And so for the left-hand, so I'll just write the formula over here for a minute. So electric field in general is equal to KQ over R squared. So for this left-hand side, if I was to do it, I can say it's KQ1 over R1 squared, where my Q1 is equal to this charge, and my R1 equals that, whereas my R2 equals this over here. So that must be equal to KQ2 over R2 squared. Now, K's cancel out here, which is nice, and I want to figure out what is this charge Q2. What is the charge at big Q over here? That's my Q2. So, Q2 in this case, if I just do some rearranging, multiply this up to the other side, it's going to be equal to Q1 R2 squared divided by R1 squared. So in this case, that's 1.2 microcoulombs multiplied by, so 0.22 all squared divided by 0.18 all squared. And if I put that in the calculator, I get plus 1.8 microcoulombs. And I just put in the plus here to make sure that they knew that I knew it was a positive charge. So that's in microcoulombs. Okay, let's do question 4. So this is on page 8, and how this is going to work is we have got lead, and it is undergoing, they've told us it's beta minus, so we're going under beta minus decay. Oh, well, we're capturing an electron, which is a beta minus particle, to get, is it thallium? Yep, thallium plus neutrino. And they've told us that thallium is 205.81. And they want us to fill in all these little, I guess, boxes on the left-hand side here. So neutrino has no charge, no mass. Electron, technically it doesn't have an atomic number, but in nuclear physics we say that it has atomic number -1 because essentially when this captures one of these electrons, a proton will be turned into a neutron. So we'll have one less proton number and the mass number will stay the same. So the mass number over here should be 205 and this one's 0. No protons or neutrons here. And then we must have had one more proton to start with, so that way we can lose one and turn it into a neutron over here. So this is going to be 82, and that makes all my numbers add up really nicely. Now part B, this one's an interesting one. It's really a worded explanation question. So they're saying the neutron number here is significantly larger than the proton number, and that's true. So the neutron number here, we don't actually have to calculate it, but if we wanted to, we could. It would be equal to our mass number. I'm just going to call that capital M for now, though I don't think that's really convention. So that would be 205 minus, in this case, what are we looking at, 81. So that looks to me like it's going to be 124, which is much, much bigger than 81. And so they're asking, why does this happen? But they're saying that we need to explain it in terms of the forces acting within the nucleus. So within the nucleus, there's two forces acting. So first of all, because there's all of these positive protons around, there is electrostatic repulsion. And that is pushing everything outwards. That's our electrostatic repulsion. But then there's also the strong nuclear force, and the strong nuclear force is pulling everything inwards. And so the strong nuclear force needs to be more powerful than the electrostatic repulsion for the nucleus to be stable. So in this particular case, the nucleus is stable because with more neutrons, because the neutrons are providing more attraction force, more of that strong force, without providing any extra electrostatic repulsion. So if you added more protons, there would be more positive charges repelling each other, and that would make the electrostatic repulsion stronger, and that's not going to make the nucleus more stable, whereas adding more neutrons does make the nucleus more stable because it increases that strong force. So that's my answer that refers to the forces acting in the nucleus as they asked. And for this part here, they're asking us to draw on this graph some alpha and beta minus decays. So it goes alpha, two beta minuses, then another alpha. Now, they've been a little bit nasty here because, for a couple of reasons. One, they put neutron number here rather than mass number, so that's probably going to throw a few people. And then the other thing they did is they made the scales different. So this is going up by 2s on this axis, and this is only going up by 1s. So in alpha decay, we lose 2 protons and 2 neutrons. So losing 2 neutrons means going down 1 step, according to this. And losing 2 protons means going left 2 boxes. So that's our first arrow. Then, when we undergo a beta minus, we lose a neutron and we gain a proton. So it looks like this, and then we do it again. So we have 2 of those little arrows. So note, I've moved down 1 and across 1. And then I undergo alpha again, like that. So that's my answer for that question there. Okay, so now we're up to page 10 and we're on question 5. They're asking us to describe 2 ways in which standing waves differ from travelling waves. So standing waves occur essentially when you have a wave that's trapped in a medium, so it continually reflects off one boundary to the other. So for example, let's suppose that we've got a nice pipe like this, and some sound goes into this pipe. Essentially, the wave goes into the pipe, and then when it gets to this end here, because it's got this open edge, it essentially reflects off this. Then it comes to here and it reflects. So it keeps going backwards and forwards, it's trapped on the inside. And so that energy is also trapped. Whereas in a travelling wave, for example, a travelling sound wave, then that energy can just keep going, it doesn't reflect. So the energy is free to keep propagating and the energy can move. Something else that's different between the two, if you've got these reflections off the boundaries, you can actually get resonance to occur. So that can happen in a standing wave, and that can't happen in a travelling wave. Notice that you can get constructive and destructive interference here, but you can also get it with travelling waves. Because if you had 2 waves coming out like this, these waves could still constructively and destructively interfere with each other. So I didn't put that down. But note, you get nodes and antinodes here. So often in the pipe, you like to imagine you've got a wave like this. That doesn't actually show you what the wave looks like. It just represents the particle displacement. So this one's moved a lot, this one hasn't moved, this one's moved back that way. So these nodes and antinodes can occur in standing waves. So that's another difference between the 2 waves. Then in part B, part I, so this is 5BI, they're asking how does a standing wave form, or outline how a standing wave forms in this tube. So we've got some water inside a big container, and then we've got a tube that we're putting into that container. So the way that I would say it is that you've got sound waves which are travelling into the tube from the speaker up here. But then when they get to the water, this is essentially a closed boundary. So they're going to reflect. So they reflect this way. But then when they get to the top here, they reflect off the open boundary. So you formed a wave in there. And then I'd just say that it's possible for this reflecting wave, if it arrives in phase with the next wave coming in from the speaker, you can have constructive interference, provided that you have the correct number of wavelengths going from the top here down to the water level there. And so that means that you can have a resonant frequency if this tube is the right length such that it matches the loudspeaker. Okay, and then in the next one, so B part 2, they've got this diagram and they've drawn something that's, so this thing's full of water and we've got a pipe in the tube here. And then they're asking us to put the position of any nodes in the tube. So we're going to have, so no, this is when the maximum is heard a second time. So first of all, as we're putting this tube into the water, notice the tube actually starts out low. So it starts out lower like this, and then we're raising it out of the water until you get to a maximum. So in this particular case, when it's really small, you can actually get a maximum here. So this maximum would occur when this sound source coming up from above, it has a fixed wavelength. That wavelength won't change. So when you have a wave that looks like this, so it's a antinode here, then it has a node just here. When it reflects off the fixed boundary, it picks up 180 degrees of phase. So when it comes back out here, it's actually back in phase again. And that is a constructive interference. So you might remember that if you have one pipe where there's an end closed and one pipe that's an end open, if you've got 1/4 lambda plus n lambda over 2, that's constructive interference. So we're looking at this case where n equals 0, and you've got this little wave in there. So that's actually 1/4 wavelength. So that's the smallest length of the tube that you can have constructive interference. Then if you pull it out further, then you can essentially have a wave that looks like this. So it still starts the same, comes to the other side, and then it reaches one of these nodes over here, and then it reflects off like that. That is essentially the case where n equals 1, and that's where you have your second maximum. So in this case, you have 3/4 of a wavelength going downwards in the pipe. Okay, so in this particular case, they're asking us where the nodes are. So we're meant to draw in those nodes. So the first node, if you like, is here. So that's actually 2/3 the way up the pipe, and the other node is just here on the surface of the water. So that's where I would draw. I would just put a dot to indicate where those nodes are heard, or where those nodes are when the maximum sound is heard. Okay, then for part 3, they want us to calculate the frequency, because these wavelengths are actually the same here. So what we can do is they've told us the difference in length here, going from here to here, they've told us that's 0.37 meters. So that 0.37 meters, that's equal to the difference between this 1/4 wavelength and this 3/4 wavelength. So the difference between these is actually a half wavelength. So half of a wavelength is equal to the 0.37 meters. So that means the wavelength is equal to 0.74 meters. So then we can calculate our frequency. So our frequency is equal to V over lambda. So our frequency here, well, we've been told that the speed of sound is 320 meters per second, and we know that the wavelength is 0.74 meters, so that means our frequency, when I divide that by that, I get 432 hertz. Okay, we're getting close to the end now. Let's have a look at page 12, and let's have a look at question 6. Okay, there's a lot of information to take in here. I'll let you read the paper first. But essentially, what they've got is they've got a circuit where rather than having a normal battery, they've got a PV cell. But I'm still going to treat it as a battery combined with a resistance like that. So all of that together is my, if you like, solar cell or my PV cell. And then there's some external resistance on the outside, like that. Okay, and they're telling us a few different things. So they're telling us the output of this is 21 volts. So this drop across here is 21 volts, whereas the entire thing altogether, so going from like there to there on the outside, is 14.5 volts. So that's the voltage from there to there. They've told us that the current that is running through this in the circuit. So that current I is equal to 0.9 amps. Now, no, none of the current's actually going to go through here. I'm just using that to show where our voltage is. And they've asked us, why is this output voltage outside different to the voltage of the PV itself, the EMF of the photovoltaic cell? And the answer is because of this internal resistance here. I'm going to call it little r, as opposed to our external resistance, which is big R. So because there's an internal resistance, that means that some of the energy is lost across this when there's a current flowing through it. So that's why we have different voltages. Now they're asking us to calculate the internal, so that's part A. In part B, they ask us to calculate the internal resistance, so that's the little r just there. Now the formula, I guess, that we're going to use here is that our EMF is equal to I, so little r plus big R. Now, there's a way we can make this simpler, and the way I'm going to do it is I'm just going to expand the brackets here. So I've got I little r plus I big R. Now from Ohm's law, this I big R here is just the voltage drop across big R. So the voltage drop across that is just the 14.5 volts. So all of this is essentially like that V just here. So then I want to solve for internal resistance. So I'm going to bring that V to the other side. So I've got epsilon minus V equals IR. And then what I might do here is I'm just going to divide both sides by I. So I get R is equal to epsilon minus V over I. Epsilon's 21 volts. Voltage is 14.5 volts. Current 0.9 amps. So when I do that division, I'm going to get 7.2 ohms as my internal resistance. Okay, so let's do a new page, and so now we're on to the final page of the paper, which is nice. So here they've given us a measure of the efficiency of the photovoltaic cell, so the energy available to the circuit, so that's the output energy, so that would be equal to the power coming out of the circuit, and power is voltage times current, and remember we actually have that information already from the previous question. So that was our 0.9 amps multiplied by, to that resistance it could provide 14.5 volts. So this, if you like, this is the energy available to the circuit every second. That's going to, when you multiply this out, you get 13.05 watts. And then we've got to divide that by the amount of energy arriving at the photovoltaic cell's surface every second. So the way that I can figure this out is, this is kind of going actually back to a waves topic. I've been told that I've got a surface which has a particular area. Now they haven't actually told me the area, but on the previous page they did tell me the dimensions of this panel. So they said that it was 450 millimeters, or if you like, that's 0.45 meters. And this one, if I convert straight away, well, it was 350 millimeters, but I'll just make it 0.35 meters. So I can figure out the area here just by multiplying those two things together. So, but then once I know that, I can use that the intensity or the power delivered to that area is equal to the area multiplied by the intensity of the sunlight. So in this case, they've told me the intensity. They've said that the intensity is equal to 680 watts per square meter. And I can calculate that area. It's going to be the 0.35 times the 0.45. So in this case, my power is equal to 0.35 times 0.45 meters, all multiplied by 680 watts per square meter. So in this case, that's 107.1 watts. So then to figure out the efficiency, I'm going to use the fancy Greek letter eta. It's going to be 13.05 divided by 107.1. That gives me 0.122, which is equal to 12.2% efficiency. Okay, and now they've got, they want us to state two reasons why future energy demands will be increasingly reliant on sources such as photovoltaic cells. So I've put my two reasons as: reason one, the world will run out of non-renewable sources of energy like fossil fuels and eventually nuclear power, because that's also non-renewable. But renewable sources like solar will then be required because the other ones have run out. And my second reason was photovoltaic cells don't produce CO2, and a lot of countries are trying to reduce their CO2 emissions to reduce climate change. So therefore, there will be an increase in reliance on forms of energy which do not produce large amounts of CO2, like solar. Well, that's the paper. Good luck with your studies.